Welcome guys. Today I am going to talk about transition metals. Normally transition metals show several fascinating features, and to students, inorganic chemistry is a boring subject and inorganic chemistry is a subject of mocking. So my honest try in this video is to teach you the fundamentals of transition elements, so that by seeing one particular transition metals itself you can feel that what kind of reaction that metal can do. That is my purpose, and I am going slow in this video so that you can understand nicely. Even if you don't understand, you repeat the video, and eventually if you have some questions, please feel free to put that in comment box. Thank you. Let's start. Look, the modern day chemistry is mainly based on transition elements. Mainly, not 100%, but mainly. So necessary question comes, what are the elements called transition elements? As per definition, we can say that those elements called transition elements who is having incompletely filled D subcell or F subcell either in elementary state or in ionic state. Okay. So in the periodic table we have whatever elements, they mostly use total 3 d orbitals and 2 f orbitals. We will see later on, but to understand the definition of transition element, we will go through two examples, that is copper and zinc. Copper with atomic number 29, and in the right hand side the electronic distribution has been given, and zinc also is there. So in elementary state both has 3d10 system, and it is not here the D is not incompletely filled. So in the elementary state these two cannot be called transition metal, but in ionic state we have two type of iron for copper, and one is copper 1 and another one is copper 2. So copper 1 is again 3D system, but copper 2 is 3D9 system. So the definition is satisfying for copper. But for zinc we have only Zn2 plus, and still that is 3D10 system, so zinc cannot be called as transition metal. In this slide I have elaborated that the transition elements property arised because of 3D. There is one row from scandium to copper with atomic number 21 to 29, and because of 4D we have yttrium to silver with atomic number 39 to 47, and because of 5D we have hafnium to gold from 72 atomic number to 79. So here we have total 26 transition element arise because of incompletely filled d orbitals. There is something called inner transition elements which arises because of incompletely filled f orbitals. One are lanthanides and another is actinides. So lanthanides are total 15 elements starting from atomic number 57 to 71. This lanthanide name comes from lanthanum element, the first element. In the similar way, actinides also start from actinum with atomic number 89 to Lr atomic number 103. Here in this slide I have given the general features which DO block element shows. First, atomic and ionic radii changes very slowly along a row of the transition element. Ionization potential and electronegativity also changes very slowly along a particular series. The third point is this kind of elements show several oxidation states. This is a very important point. The fourth one, their chemistry is dominated by complex formation. This is also important point. The fifth one, transition metals often form colored compound. And the sixth one, many compounds, transition metal based compounds are paramagnetic. Seventh point is transition metal are high melting and high boiling metals. And the eighth point is the sum of the metals or their compounds act very efficient catalyst for several organic and inorganic reactions. So to understand why transition metals have these fascinating features, we need to go back to the electronic distribution of the atoms. As you all know that first row transition element starts from scandium, and just before that we have two elements which are non-transition element called potassium and calcium. We need to check these two elements also to know the transition elements properly. So here I already made ready the electronic distribution scheme and with the orbital pictures or orbital lobe pictures. Here it is potassium, and where the sign of potassium has given, let imagine there is the nucleus sitting in the left corner, and based on the energy level from left to right, say the energy is increasing of the orbitals gradually from 1s, then 2s, then 2p, gradually to 4s and 3d. That means the right hand side orbital is having highest energy and the left hand side orbital is having lowest energy. And lowest energy means close to the nucleus, and highest energy means farthest from the nucleus. If we recall the Aufbau principle, Pauli's exclusion principle, Hund's rule, and based on those rules, if we start distributing the electrons, so gradually in this way, first the lowest energy orbital is 1s, 2 electrons come here, next level is 2s, 2 electrons comes here, next 2p, within 2p we have 3 lobe, px, py, pz, and as per Hund's rule, all px, py, pz will fill up with 1 unpaired spin. Then another 3 electron will come by spin pairing this way. Then electron will go to 3s in the higher energy, one after another, then 3p this way. Now what electronic distribution we got? It is argon's electronic distribution with the atomic number 18. For potassium, the atomic number is 19. So now the question arises, where the 19th electron comes, whether it is in 4s or in 3d, because as we know, normally the lower principal quantum number one should be in lower energy level, but in reality the 19th electron is going to the 4s. So we will go with the reality, means 4s is having the inference from here is 4s is having lower energy than 3d, that's why the electron is going to the 4s. If we go to calcium, starting with the electronic distribution of potassium, then calcium is having one more electron to leave there, so it comes again to the 4s. This situation, that after argon, the two electrons, one for potassium and two for calcium, comes to the 4s, indicating that 4s is sitting in lower energy level than 3d. But here in next slides we will discuss the fact that if 4s is sitting in lower energy level, then when this kind of means for transition element also, after filling up 4s, scandium, vanadium, etc. till the copper, the next electrons all will come to the 3d. Okay, this way. Well, the entire scenario is indicating that 4s is sitting in lower energy. Okay. Now the question arises that if 4s sitting in the lower energy, fine, but when this kind of metals is becoming ion, then why the electron leaving from the 4s first, then from the 3d? Because as per our understanding, that the orbital which is farthest from the nucleus, the electron from that orbital should leave first, but electron from the 4s is leaving. Why it is so? Electrons entering in 4s first, as well as electron leaving from 4s first. Why? In next slide we will discuss that. Yes. So here I have given two cutting of the pictures, two graphs basically. The left hand side one is the, you see here, here where my arrow is checking, nucleus is sitting here, and this is x axis, it is showing the distance from the nucleus, radial distribution basically, and in the y axis probability density of finding an electron. So we can see that 4s orbital is penetrating to the nucleus. Okay, it is getting some sort of mixing up with the nucleus, with having more interaction with the nucleus. That's why 4s orbital will get more stabilized when both the 4s and 3d is empty. That time energy level of 4s will be less than 3d, because 3d probability density maxima is sitting far away from the nucleus compared to 4s. So 3d energy level will be higher and 4s energy level will be in lower place. That's why when electron comes to fill, in case of potassium and calcium, it will fill up the 4s. But after that, from scandium to copper, when electron will start filling the 3d, then because of poor screening effect available of 3d orbitals, 3d electrons, the effective nuclear charge rises sharply from scandium to copper. An increase of effective nuclear charge implies that nucleus and 3d electron is gaining the attraction force, and more it gains the attraction force, more the 3d electrons go closer to the nucleus. and more it is going closer to the nucleus. One time will come when the 3D energy level will drop even below the 4s energy level. When it happens, after that, if any external oxidant comes to get the electron from the transition metal, that time it will see that 4s is the farthest away from the nucleus, and 3D by that time went inside, and 4s get exposed to the outside, and the external oxidant will grab the electron from 4s first in this scenario. That is why we see that 4s, while electrons are filling the orbitals, 4s will get filled fast because of it is sitting in lower energy, and when oxidant is taking electron out from the metal, transition metal, then also 4s is sitting outside, farthest outside of the nucleus. Okay. And just why, let me mention it, why here it is psi square, because psi is the wave function which is having both side value as plus, 0 and minus. But you know that when you talk about probability, you cannot talk minus probability. Probability is either 0 or probability will have some positive value. That's why psi square, if we take the plus portion of wave function, also will give plus, and minus wave function also will become plus. That's why psi square has been taken. And in the right hand side picture, it is showing the value, means energy level of the different orbitals along with the increase of atomic number. So here I can show a particular zone. Here you can see the 3D energy level is higher than the 4s. That is sitting around that very same potassium and calcium, scandium level. And one time we'll see that 3D and 4s having same energy kind of thing. Anyway, with increase of atomic number, 3D will drop more and more towards the nucleus. Means the energy level will drop more and more. Okay, with increase the atomic number. Now come to the features of transition metals. This is the first feature, that atomic and ionic radii changes very slowly along a particular series. Well, why slowly? Because the principal quantum number is not increasing. All the electrons are coming one after another to the 3D level. So principal number is not increasing, means overall size is not increasing. Whatever little bit size difference we are seeing, that is because of increase of effective nuclear charge. From titanium to copper, effective nuclear charge increases gradually, and that is why the outer electrons, orbitals containing electrons getting shrink little bit towards the nucleus. That is why radius changes, that is also very little. Now check the change of ionization potential and electronegativity. That is also because of increase of effective nuclear charge, but size is not increasing too much. In this case, from titanium to copper, you will find the increase of ionization potential of the electron, as well as the increase of electronegativity also from titanium to copper has been shown here. You can go through the value. Now the most important point I will discuss, and this is the last point of this video, and remaining transition metals features we will discuss in next video. Otherwise the video will become, if I try to discuss all the features in the same video, means video will become very lengthy. Anyway, so to understand that why transition metals give so many oxidation state, we have to go back to the non-transition metal again. That what is the difference? Certain difference obviously has between the non-transition and transition metal. That is why this kind of features we see within the transition metal, but not in non-transition metal. For non-transition metal, we often see that one oxidation state, like sodium is +1, calcium +2, aluminium +3, like that. Aluminium you will find aluminium +1, aluminium +2, aluminium +3. This way it will not go. Straightway you will see aluminium +3. Straightway you will see calcium +2. Straightway you will see sodium +1. Because for non-transition element, whatever valence electron they have, they either will throw those electrons out and get the inert gas electronic distribution below its level, or they may gain some electron to get the inert gas distribution of the higher level. Like sodium, it becomes +1, it will get neon distribution, and if chlorine is getting gaining one electron, then it will become argon distribution. And these electrons business all happen in s orbital or p orbital, and s and p orbitals are always degenerate. Within p, if you have px, py, pz, all these three having same energy level. Any outsider, any external oxidant will see px, py, pz in same way. That oxidant will not have any partiality to any lobe to get the electron. But for transition element, in the valence level you have ns electrons as well as n-1d electrons. And since principal quantum number itself is different, so you can expect some sort of energy gap between ns and n-1d. Whenever you see energy gap, then for the oxidant there is a possibility arises to get the electron selectively from ns or from n-1d this way. And if we again focus on n-1d, then normally in elementary state all the lobe of the d orbital are degenerate, means all the lobes having the same energy level when it is in elementary state, but when it is under a crystal field, then d orbitals will no longer be the degenerate. It will split. In the next slide we will try to discuss it. See, in the left hand picture I have shown all 5 lobe of the d orbital, like dxy, dxj, dyj, dx square minus y square, dz square, these 5 having the same energy. But under a crystal field, here I am showing, suppose it is octahedral crystal field, so there it will split in T2G and EG. In T2G will get stabilized, EG will get destabilized from the ground level. The point is, the amount of stabilization T2G gets, the same amount of destabilization EG will get, so that the total will become 0. Suppose T2G get 4 unit stabilization. Now in T2G we have 3 lobes, so 4 into 3, total 12 unit stabilization we get from T2G. The very same 12 unit destabilization we must get from EG. Now here in EG we have 2 lobes, every unit will destabilize by 6 units, so that 2 into 6 equal to 12. This way I have shown here octahedral field, but there are several other kind of field like tetrahedral field, distorted octahedral, distorted tetrahedral, kind of when more and more you go to complexity, there will be obviously more complex scenarios. But for the time being, I am just for the reference purpose I have taken the octahedral field. In this video, my aim is just this much, that you should know that all the d orbitals are means from outsider oxidant, all the d orbitals are not the same, unlike p orbitals. So in that case, if we go with the octahedral crystal field, then in the scenario we get three energy level, like ns energy level, and in n minus 1 d energy level we get one eg level and one t2g level. So when oxidant, whatever we are providing, when it is weak, then it will take electron from outside 4s. Further, if we increase the strength of the oxidant, then it will come to the eg level, and whatever electrons are here it will take. If we further increase the strength power of the oxidant, then it will look at T2G to get the electron. So by controlling the oxidant's capability, we can selectively pull out the electrons from step by step from several levels. And when we will discuss individually few elements, then your vision will be more clear. So like potassium and calcium, these are non-transition element, and they have a valence electron in 4s. Never mind 1 or 2, they will go. When oxygen comes, outsider oxygen comes, they will go. But now start with scandium. Scandium has 3 valence electron, titanium has 4 valence electron, and vanadium, iron, copper, like whatever the electron has, it has shown here. Next we will go to discuss individually. See, I already mentioned that more and more electron introduced in 3D, that electron will increase the effective nuclear charge, and it will pull the 3D to sink below 4s. So first scandium, this is the first electron which introduced in 3D, and effectively what happens, it is helping to 3D to get synced. And what happens in reality, that because of one electron, the gap between 4s and energy gap between 4s and 3D, like this gap, will become very less. And for an external oxidant, the distinguishing between 4s and 3D cannot be done. External oxidant will feel all are same, and as a result, for scandium, all 3 electrons goes together, and we get only +3 oxidation state for scandium. For titanium, the major oxidation states are titanium +3 and titanium +4. Although +2 is also reported, but see, the d orbital gets split. One will go to Eg, one will go to T2G kind of thing. But the Eg level and 4s level, definitely T2G obviously goes below, the energy level goes below, but the Eg level and that 4s level energy gap in practical is so less that it is very tough to keep titanium in +2 state. Okay, because an oxidant which is taking 2 electron from 4s will take an electron from Eg level sitting at 3D. That's why titanium +2 oxidation state is rare. But titanium +3 is common, and titanium +4 also stable. And the gap, energy gap between 2 orbital can be reflected from the E0 values. Okay, titanium 3 plus and titanium 4 plus in between. In this transformation, you get E0 value is 0.10. That means there is some gap available between two d orbital. In case of iron, Ap3 plus to Ap2 plus, this half cell shows 0.77 volt E0 value. That means it is much bigger than 0.10. That indicates that, well, let's go to the next one. This way titanium will go. Anyway, so for vanadium, we get several oxidation states, but the bold one are the major oxidation state. Okay, so we have plus 5, plus 4, plus 3, plus 2 is unstable, plus 1 is unstable. That means what? That plus 3 means what? 2 electron will go from 4s and 1 electron will go from 3d. And this is major, this is powerful oxidation state. That means in somewhere the Eg level of 3d and 4s level come very close. That's why vanadium plus 2 is unstable. Although it is available, but very unstable. Once 2 electron goes out from 4s, the third electron by the very same oxidant can be taken. That means Eg and 4s energy level are very close, almost indistinguishable, almost. So this way it will go together. Then if you increase the power of oxidant little bit, it will take another electron, leads to vanadium plus 4. Little bit more power you provide to the oxidant, it will take another electron, leads to vanadium plus 5. Next, come to the manganese. So manganese has 7 electrons, valence electrons, and we find manganese in plus 7, plus 6, plus 4, plus 3, plus 2 and 0. These many oxidation states are available. Now here in the bottom there is something called Latimer diagram. The strategy of writing this diagram is that the highest oxidation state you should write in the leftest corner, and the lowest oxidation should be there in the right side, the rightmost corner. So you just follow how I wrote this one. Anyway, in each transformation, here the potential value E0 value has been given. So if you directly move from power manganate to Mn2 plus, you get 1.51 volt E0. Okay, and if you go by breaking the method, like Mn plus 7 to the Mn plus 6, then Mn plus 4, then Mn plus 3, this way you cannot match just summing up the E0 values, because delta G gives free energy is the state function. So delta G will have fixed value whichever path you follow, and delta G 0 equal to NAP 0. This way you can count in the first part, like MnO4 minus to MnO4 2 minus, it is 1 electron system, so 1 into 0.56 plus MnO4 2 minus to MnO2, this is 2 electron system, so 2 into 2.26 plus MnO2 to Mn3 plus, it is 1 electron system, so 1 into 0.95 plus Mn3 plus to Mn2 plus, it is again one electron system, so again 1 into 1.15, okay, into altogether into F, because F is there, all, and the result is 7.5 per F. And if you take the direct reaction, this is Mn over minus to Mn2 plus, this is 5 electron reaction, so bring 5 here into the E0 1.51 F, so it is together, it is coming 7.55. This way you can fix it. So for manganese, first, for manganese, to get Mn2 plus, first 2 electron will go from 4s like this, and it is stable. That means the top Eg level of the 3d orbital and 4s level having some energy gap. That's why Mn2 plus is stable. Now increase the power of oxygen little bit, you will get Mn3 plus. Increase the power of oxygen little more, you will get Mn4 plus. Then you will get Mn6 plus by increasing power of oxygen. Finally, most powerful oxygen will give you Mn7 plus. This way. In this slide, I talked iron and copper. I just want to mention you that there are few elements missing like chromium and nickel and cobalt nickel. Point to be noted that whatever I am giving, this is for example purpose. Okay, I need not to mention all the element. For them also the similar thing will, similar answer, similar explanation will be there. Okay, so for iron, first 2 plus 2 and plus 3 state are stable, so first 2 electron will go first from 4s like this, and since this is little bit stable, that means there is some gap between the Eg level of 3d and 4s energy. You increase little bit power of the oxidant, then you will get plus 3, and you have to increase the oxygen's power quite more, then you will get plus 4 and plus 6. Now if you look at copper plus 1 is quite stable, that means there is fairly energy gap is there available between the 3d and 4s. First electron will go from 4s, then second energy, if you increase the power of oxygen, second will go from 3d, and third will go from the 3d. Now I am finishing this video here. Please repeatedly see this one to understand in proper way. And one suggestion, please subscribe the channel and click on the bell button so that you continue to get the updates whenever I put new videos. Thank you.